Hello, ladies and gentlemen. I'm Khatri. I'm a structural engineer, and I welcome you to my report number 3, where we will look further into foundation issues as it relates to the Champlain tower collapse. I very much appreciate all of your comments, and thank you again for watching this new report on July 12th, 2021. So these are some links to my previous reports. I've done 2 reports on the Champlain tower collapse, and I've also done a report a few years ago on concrete buildings, which I encourage you to take a look at. And this is for your information to see some of the background that I've done on this topic. So as an introduction, I want to be clear on exactly what I'm presenting. I am not working for any particular organization here other than myself and my company. I don't represent any government agency. This presentation is for information only based upon my experience and education, having been in this industry for over 39 years. And I'm providing my field notes from my first site visit on this project on June 26th, 2021, clarifying this as report number 1, as there will be subsequent reports to follow. For report number 3, we continue on with where we started from report number 1. These were the initial observations that I noted in the first report and the second report. None of those have changed, and we'll be picking up from the last report moving ahead. In report number 3, we're going to focus on topic number 2, which is looking at the footings. The reinforced concrete driven piles with a concrete pile cap. There'll be additional reports on topics 3, 4, and 5. Today we're going to focus on just the foundation. There are some observation notes that I want to bring to my fellow engineers in this business, and hopefully it will help us to look at other structures that may potentially be showing signs of collapse or failure that we can prevent from happening. This is an excerpt from the as-built plans from the structural engineer for this project on the foundation design, and these are their notes. The foundation system being used here is a pile cap with driven piles that are driven into the ground, and I want to discuss this foundation system with some brevity and give you an understanding of how this system works. And an important note is that the most important document right now that we are missing from the file is the soils report. That is by far the biggest piece of information that I haven't seen, which will tell us what the depth to bedrock is, tell us what the water content is, the moisture content, the compaction level. That is missing from the file right now. So foundations on piles, let's understand how these work. You have a cap which is connected to a system of, in this case, driven piles. The cap brings the loads in from the vertical columns. There's an axial load, there's a horizontal shear load in the event of wind, earthquake, or hurricane forces, and there's an overturning moment. These forces are resisted by the piles through a system of skin friction and end bearing. And there's a line that I've drawn there which is a schematic diagram showing bedrock. So hopefully these are driven into bedrock. We don't know that. We don't have a soils report, so we can't say if there is bedrock. I'm hoping there's bedrock. But the piles transfer those loads from the cap into the soil on its skin friction and through end bearing. And this is important because the relationship between the skin friction force, the pile, directly affects how that cap is going to react. And if you were to have a slippage of a pile, this would cause the cap to rotate, which would cause the columns to move. This is something that is never considered in any design process. We don't assume that our pile caps will be moving or rotating. I bring this issue up because I do a lot of work in the wind tower industry, and in the wind tower industry, this is a common interest because wind towers are very tall, and so the issue of pile cap rotation is considered in our design process. It is not considered in the building design process. So what is a driven pile? A driven pile is considered like a stick that you are then hammering into the soil. And you hammer it into the soil to a certain depth to achieve a certain amount of compression value. In the case of the Champlain Tower, the driven piles were driven to 50-ton capacity, which is 100 kips or 100,000 pound capacity per pile. And they're driven into the ground, and the deflection relationship between the pile and the soil that it goes into is very important, because you can drive a pile into the ground, and if you don't hit bedrock or you don't hit solid enough material, the pile could still be loose. And that's all contained in the geotechnical reports at the time when the piles were driven. And clearly we don't have that information right now, but the concept is that the pile is hammered into the ground and then is supposed to be stable for the duration of the building. So this is my what if scenario, and again, this is not considered in conventional building design. This is considered when we're designing tall towers, such as wind towers, where the rotation of the foundation is considered to happen. So here I'm posing a situation that if one pile or a group of piles were to sink by just a little bit, and you'll see how much that little bit is, it's less than an inch, it would cause the cap to rotate, which would cause the column to go off center line. And what you're seeing here is point B is deflecting down a certain distance delta, which causes a rotation of the cap theta that is then transmitted into the column rotation theta, which will affect the column relationship between the base at the foundation side or the garage level to the first floor. And we're going to take a look at the mathematics of that in a moment. So if we were to have a modest rotation, a very small rotation, and I've just used an example here of 1/4 of a degree, and our cap had a horizontal distance of, say, 15 feet, which is pretty close to what the Champlain Tower has in their caps. The pile caps are 14 feet. I'm using 15 feet. That translates into a deflection of roughly 3/4 of an inch, or 0.79 inches. If you were to project that deflection across the height of the building, now I understand that we have rigid diaphragms, we have concrete diaphragms that are bracing that column from shifting. I understand that. But just to understand the geometrics involved, that less than 1/4 of an inch, less than 1/4 of a degree, or 3/4 of an inch roughly of deflection will translate into about a 1/2 foot of movement, 6.28 inches, at the top of the building. If that were to happen, that's a very serious deflection. Now, we do have rigid diaphragms. We have a lot of bracing elements that are preventing that from happening. What it does do, though, is it puts tremendous strain on that first story column, because if its base is rotating, it will cause all kinds of secondary stresses to develop in that first story column. Secondary stresses that it's not designed for, that it was not considered to happen in the original design process. And so if we were to have just even modest deflections, it will cause column rotation at the garage level. It will cause distortion of the column on the first floor. It will aggravate P delta moments, which potentially lead to buckling and instability failure, and it will be weakening the upper story columns. Now, that mathematical equation of how much deflection and how it relates to the upper story columns gets rather detailed, and I am looking at that right now. I will produce some analysis on that and share that with you in the coming weeks. But this is a consideration that is not considered in conventional design and is potentially a very potentially strong root cause failure that could have happened. I'm not saying it did happen. I'm not saying it's definite because I don't have enough information. But I've done enough work in this industry on different types of tall structures that I can certainly consider this to be a potential contributing cause of collapse. And it's something that we need to look at as engineers that are working in this industry we do need to look at this on other existing buildings, because this is a point of failure that can be measured. This is a root cause that can be measured in the field, and we can document it, and we can potentially predict a collapse before it occurs. Because if a building is sinking non-uniformly and the caps are rotating, we can measure that using instrumentation, and then we can tell our clients whether or not their building is shifting. And so here I propose a system that we are currently using in my firm for clients to evaluate their existing buildings, and that is a system of structural monitoring to check the floor slab deflections. And I've shown a schematic diagram here which shows a high-rise building sitting on a subterranean parking structure, and we will, meaning my firm, will survey the slabs to see whether or not they are moving. We will do a full-scale survey and measure the relative deflections of that subterranean parking structure to see if it's shifting, to see if slabs are settling, and to see if they are level or are they rotating. And then part two is we will check the column alignments. The column alignments are very important. Obviously, if a column is not vertical or a column is distorting, that's a cause for concern. Now, it could be that those columns were not aligned to begin with. No building is built perfectly straight and square. I understand that, and we have to accept that. But there are tolerance requirements. There are tolerances that we can check it against. And this is the area where I think we as structural engineers should be looking at this when we're called in to look at a building. How do we know whether or not that building is potentially in a collapse mode, may have already started to collapse and we haven't noticed it? This is an analytical procedure that we can do in the field to measure and see whether or not that building is moving. And I highly advise that we do this as part of our scope. So for this report number 3, what are my conclusions? Well, the first conclusion, which is very important, is that we still do not have the most important document now that's missing from the file. Is we don't have a soils report. We don't have any water measurements, moisture content measurements in the soil. We don't know the depth of bedrock. This is a huge missing piece of information, so we can't certainly make any definitive conclusions until that information is made public. We don't know the foundation cap settlement, but we know that it's a potential cause of failure. In the file that I examined that's publicly available, I didn't see any as-built measurements or continual structural monitoring measurements of the foundation. And this is essential for monitoring the performance of a high-rise building. This should be looked at on all buildings. So I highly advise that structural engineers should put together a monitoring program. It's essential for structural assessment. We should be looking at column alignments. We should be looking at slab deflections. And we should be taking these very seriously, because if they are outside of the envelope of performance criteria, this is a cause for concern and raises a red flag that we should then bring back to our owners and let them know, so that we don't have another Champlain tower collapse ever again. So as always, I always thank my audience for listening to my thoughts. I appreciate your comments. I appreciate your likes and your thoughts, and there's more reports coming. And I welcome all contributions to the YouTube page and to the LinkedIn page, and we'll share more with you in the coming weeks. And I thank you again.